say a little bit about some more, slightly more difficult material, which we'll continue with later, like next week, about the relationship between Chern-Simons perturbation theory and the Jones polynomial. So the last time we defined Wilson loops for non-abelian gauge groups. So if gamma inside of order 3 is a closed loop, okay, then the Wilson loop is defined to be the trace of the path-ordered exponential along k of A. So in other words, the trace of the parallel transport on k. And we saw that this is a gauge invariant quantity. So we can consider the path integral. So I would like to apologize in advance that I'm going to be a little bit sloppy about how to normalize the coupling constant. I can never quite remember the correct normalization. So this defines for each k a series in h bar. H bar is the coupling constant. The series is defined just by usual Feynman diagram perturbation theory. Okay, so this quantity is almost, I'll come back to this almost in a minute, and not invariant. I.e. something that doesn't change. Change if we continuously vary k. So the proof, there are two proofs. One, I've actually given one already. Variations of k can be realized by diffeomorphisms. Diffeomorphisms phi, and the Wilson we have this identity further the path integral measure is invariant under the transformation A goes to phi star A. This is a very, if we believe in the functional measure, this is the kind of argument you might like to propose. Another sketch argument on shell f of A is equal to 0, so that WKA on shell. By our discussion yesterday, if we change a knot and the curvature vanishes, the Wilson line will not change. If we vary k. And we might hope that this should persist at the quantum level. This is kind of why you might expect this to be true. Okay, so I say almost. So there's a subtlety. Which is that this expression, if we were to study the path integral for this expression, it depends on one more piece of data, which is a framing. In fact, the non-invariant, the path integral, depends on one more piece of data, which is a framing, which is the same as a vector field, so a choice of a normal vector everywhere on the knot which does not vanish. So we draw a picture of a frame knot. So here, if I draw a knot on the blackboard, I can frame it just by taking the direction of my knot and turning right. On the other hand, I can draw the same knot on the blackboard in a different way. And I can frame it also just by turning right. So as I go along here, just that way. Okay. So this is an example of the same knot. They're both, there's the circle, the on knot, but with two different framings. So in general, if I take my knot and I project it onto the plane, I get a framing by using the orientation on the plane. but that framing might depend on how we project it. So when we say it depends on the framing, what I mean, the important point is that the invariant does not change if I continuously vary the pair, the knot, and the framing. But the path integral does not change if we Okay, any questions? Yeah.
Sorry, why it has to be a normal vector? Why cannot be a tangent vector?
Well, a knot already has a tangent vector. Just like I just go along the knot. That's the choice of tangent vector up to isotopy is not really any choice. Because there's, but the choice of a normal vector, well, there's several ways to do this up to continuous variation. But I mean, in practice, the real reason is when you study the path integral, you have to do some regularization procedure at some point. And the one way to do this is point splitting. Are you familiar with point splitting regularization? So you probably have you guys only studied Feynman diagrams in momentum space?
We did position space.
You did position space? Okay. I mean, I think lots of people only do momentum space, but then it's very hard to talk about things like Wilson lines because the Fourier transform of a knot is some giant mess. Okay, if you do position space, your Feynman diagram has some vertices, and I integrate over their positions, and point splitting regularization says I don't let these positions get too close because the amplitude has a pole when these guys come together. And if I want to do this with Wilson lines, I'm going to have to slide my knot off itself. And I use this vector to slide it off itself. So in the details of how you do the Feynman diagrams, you have to make some kind of choice like this. It gets pretty, it gets very detailed and tricky to figure all that stuff out. But ultimately, that's where it comes from.
So I need the vector if 2 points on my knot are getting too close, I need the vector to tell me where to push the point for it to go through, or underneath or up.
Yes, that's the kind of thing. Let me draw. So for example, well, if I had a knot like this, I might have a. I'll say more about in details how to do the diagram expansion, but when we do the Wilson line, we saw yesterday we integrated my gauge field along the knot. So there might be one integral there, one integral there, and the path ordered exponential. And then they might exchange a gluon. That. And then when they get close together, it's a bit tricky to know exactly the singularity, it's a little tricky. And you might say, well, I regulated by actually making the first point there, but the second point on a shifted over copy of my knot. So you regulate it like that. But to do that, I needed to tell you which direction to shift. And they give you different answers. So this one doesn't give you anything because they don't cross, whereas this one, if I shift it over, the two knots cross. And I get the linking number of my knot and its shift.
How does the second argument for the path integral being a knot invariant work? As in, when we're doing the path integral, we're not on shell?
Right, but the equations of motion when you study the path integral, the equations of motion are, of course, classical. the classical thing. Let me say we're in finite dimensions. I have some integral e to the minus s of x over h bar dx. Now, if I have a vector field, then the integral of well, I can ask, how does this guy transform under this vector field? And there's two terms. How does this measure transform? That's just the divergence. And how does this quantity transform? That's minus integral 1 over h bar fx dx s prime. This is, of course, 0. Plus the integral del x f e minus s over h bar dx. So in the classical limit, h bar goes to 0, e minus s over h bar. As h bar goes to 0, this term dominates. And what we're saying, in the classical limit, observables of the form like del x s prime are 0. So this is the on-shell equations. But when I make it quantum, that gets modified by this contribution here. This contribution here is divergence with respect to the functional measure. So the fact that you can throw away things which are on shell gets modified at the quantum level to something involving divergences with respect to the functional measure. And then these quantum identities are like word identities. So here, on shell that equation vanishes, you might expect some quantum perturbation of it to lead to a similar. I mean, I agree this is a bit vague, but it's not. You have to analyze what the quantum deformation of this equation is and how it affects the variation of the knot. But it's another way to approach a proof of the statement.
Can I ask a question?
Yeah.
I'm just confused where this object lives. Where does this not live that you are allowed to speak with the frame? Because how is it going to be compatible with the? You have the field A. Are those local? Like, are you making the same locally? Because I don't know.
You're asking like why does this expression depend on the frame? Is this the question?
No, like you have a specific structure. Some principle, but no, it's not always possible for you to choose a frame.
Oh no, it's not a frame of the principal bundle.
Okay, that's where I'm like, where does this knot live?
Then the knot lives in R3, and I'm just choosing for every point on the knot, I'm choosing a normal vector.
Okay, so this is independent of this choice of the field A that I have.
That's right. Yeah, exactly. Yeah, absolutely. Although, I mean, you might ask, like, this expression, this path-ordered exponential, is defined just for the knot and does not depend on the normal vector. So what we're seeing is you have to correct that by things which do depend on how A behaves in the normal direction at the quantum level. There's some counter terms.
So it is the functional measure which could depend on that framing. I mean, in the heuristics of that formula, where is the end dependence? It should be in the functional measure.
In the heuristics of this formula, the dependence is that this expression W does not just depend on the knot, it depends on the knot plus this little normal vector. So if I apply my diffeomorphism, I can my diffeomorphism will move the pair of the knot and its normal vector around. So if I can continuously vary one knot with normal vector into another knot with normal vector, I have the same answer. But I can't, if I fix my knot, sometimes I can move the normal vector around, but there's distinct classes. So for example, if I just take this circle for S1, how many choices of normal vector of framing up to continuous variation, which is also called isotopy, are there? The answer is there's an integer's worth, because I can take my normal vector. It's hard to make it point up. I'm going to make it point up and point down. Wow. This is a terrible picture. Sorry. Guys, we should just picture in 3 dimensions. The normal vector can wind around. Okay. So it's hard to draw on the blackboard because it's a 3-dimensional phenomenon. The normal directions, I can take my vector and normalize it so it has magnitude 1. And the normal vector is a point in the circle. So I take each point in the circle and give you a new point in the circle, and I measure how many times do I wind around. And that's an integer.
So that would be that picture, but so twisting.
Yes, exactly.
Is that equal to?
Yeah. And if, for example, if you took this picture and tried to unwind it, you'd realize that the normal vector wouldn't always point in the plane. At some point, it would point up.
Sorry, so what do you mean by the vanishing of normal vector?
Oh, I mean, I just don't want it to be 0.
Yeah, but yeah, so can you give an example of the vanishing normal vector?
What's that, sorry?
I mean, an example of this.
I mean, I could take my... It depends what you mean by normal. If normal is a vector which has whose inner product with the tangent vector is 0, then the vector 0 is normal. So I just want to exclude stupid things.
Oh.
I want to exclude the tangent. The vector 0, strictly speaking, counts as a normal vector, but I want to exclude that.
I see.
So there's two things I wanted to try to explain. So one is, how does one actually do this path integral measure in practice? Like, what do the Feynman diagrams look like? And the second thing is, what does the answer look like? So I think I'd like to explain the result of Witten that this path integral gives you up to a normalizing factor, something called the Jones polynomial. So I'll define the Jones polynomial. So the first thing I want to define is the Kaufman bracket. So this is not my personal, this is a fun area of math. It's not something I personally have great expertise in. So let me me see. So given a link defined by a planar projection, let's see. So I have some, some crossings in the plane with orientations, e.g., we define the Kaufman bracket of L, which is a polynomial in a variable I will call x. So it's defined by local rules at each crossing. So if I have, this is a little bit embarrassing, but I'm actually reading the definition off the Wikipedia page. So, So it makes sense. If I have a local crossing like this, I can do two things to make it to undo the crossing. I can smooth it that way or smooth it that way. And the rule is, anytime I have my bracket invariant with a knot, well, you want to compare it to the invariant where I've smoothed the crossing in each of these ways, and I get this linear relation involving the polynomial x. So the second relation is that the on knot gives you 1. And the third relation is that the on knot union any link is equal to minus x squared minus x minus 2. So this is something which will give us a polynomial in x and x inverse So these rules make this guy x into a Laurent polynomial. Of x. Let's compute it. An example. Let's take a very simple example like this one. Okay, so now this is a knot which has one crossing. So I'm going to get sum of two terms with factors of x. So I look at the equations there. This is x times plus x inverse times, well, this is a smooth one. And next, I look at the second and third equations. This is just a circle, so this quantity gives me 1. And the other one, if I take an on-not union any link, I get minus x squared minus x minus 2 times that guy. So this is minus x squared plus x minus 2 plus x inverse, which is minus x cubed. Okay?
Okay.
Yeah.
So knots have to be thought of. I'm sorry, I have no idea of what a knot is. So I'm trying to do.
So I mean, the starting picture of a knot is just a closed loop in R3, like your shoelaces. I mean, it's not.
But for all this to make sense, I sort of have to project it, right? Because if I have a knot like this, I can always like do this and it.
Exactly. So this thing, it seems to depend on how I've projected it. So it seems to, this is not an invariant. Because this, however, what we're going to see is that this is an invariant of a framed knot. You know, as we saw, if I frame this according to how it's projected, it is not the same framing as this. This framing winds around once, and this one winds around. I mean, they're different. So it turns out that this Kaufman bracket only depends on the knot together with a normal vector.
Doesn't matter if I do this or I'm sorry. If I pass like the lower line above. If I have
I think you're inventing the Reidemeister moves. Yes, these are like, there's some moves, like given the planar projection, if I project my knot, sometimes I can change the projection and leave them just like giving me the same knot.
Okay.
And you're asking, does this change? So there's 3 moves you're allowed to do. So I was gonna. So sometimes, so a knot can be represented by a planar diagram in a plane projection in many ways. But these are related by the Reidemeister moves. Like there's 3 moves, and there's some standard names attached to the moves, but I forget the standard moves, I forget the names. So these are, first one, so the Reidemeister moves are like local moves you can do on a knot, which doesn't change it. So if 2 things cross over, I can slide them apart. Aldo, do you remember if the standard ordering of the terminologies is 1 or?
I think 1 is the little.
Oh, 1 is the writhe thing.
Yeah.
Okay. So this is 2.
Then there's the sliding.
Okay. And there's one where I flip something over.
Sorry,
Mm-hmm.
may I ask what do you mean by this equal or equivalence sign?
So this is,
Are the framing are equal or just not equal?
so here, these are moves for knots without a framing. This one here will change the framing. This one preserves the framing. So this one, so we're going to realize that the Kaufman bracket is not invariant under this.
Yes, yes.
So this changes the framing.
Because the knot that we studied in the example becomes the circle, right?
Exactly. Yeah. So but the Kaufman bracket is invariant under the other two Reidemeister moves, which leave the framing fixed. And R3, this is also called the Young-Baxter equation of statistical mechanics. I mean, the history of the Jones polynomial is kind of fascinating. Jones was studying statistical mechanics when he came across it. So here we have 3 lines. This one is going to be at the top. This one is going to be in the middle. And this one is going to be at the bottom. And I'm going to slide the one on the bottom up to the top. So I've just take this one here and moved it up. This one also preserves the framing. So if we're interested in invariance of framed knots, so, well, we see if we have a knot and we draw it in the plane, that knot has a framing because I can just turn clockwise. So where the framing comes from the plane of projection, then we only need to apply the second and third. And then the theorem is the Kaufman bracket is invariant under OR2 and OR3. So this, yeah.
So I didn't understand exactly what x was here.
It's just a variable. Ultimately, x is going to be related to the coupling constant of Chern-Simons.
Okay.
Any other questions? So why is this true? Well, this turns out to be just some little computation. You look at the definition, and you apply it to these guys, and you just compute and see what happens when you undo the crossings in all possible ways, and something cancels. So let's try and check it for OR2. So I haven't actually done this, but I'm sure it's not hard, so we'll try and do it right now. So this is equal to, we have the definition up there, and I'm going to apply it to the bottom crossing. This is x times, undo the bottom crossing like that, plus x inverse times undo the bottom crossing like that.
Does the object inside the bracket have to be or not? Or like currently it's like...
It's not.
Yeah.
So, so because it's defined by these local moves, what you need it to be is you fix some kind of boundary behavior, and then it can be anything with that boundary behavior. Right? And then I'm allowed to change things in the middle by these local moves and simplify it, but keep the boundary behavior the same. Here the boundary behavior is there's 4 points. So
Seems.
what's it? Let's see. You know what? I realize there's probably, because this crossing I've written over there is not the same as this one. They probably differ by their sign difference. Can I take the cap and bracket?
So if you rotate,
Oh yeah, of course.
so it exchanges the two.
I see. Yeah. So this is. Gotcha. Thanks a lot. Okay. So this, if I do this one, so this is x times. So as Aldo said, I need to exchange the two things because this is an overcrossing, not an undercrossing. So this is promising, right? Here I have 1, and then plus x inverse times
If it is second, it should be x, so x minus x, second.
Oh yeah, thank you. That's going to be an x squared. And this, the rule about adding on a circle, you see there's a circle going to appear there. And hopefully that's going to cancel with that x squared. And with the other term here, which will be an x minus 2. So this one is also that crossing, so that's going to be x times x inverse plus x okay. So that's this thing plus x squared plus x minus 2 minus x squared plus x minus 2. Great. It actually worked. I'm kind of surprised. Yeah. I'm surprised they didn't make a mistake. Not that Kaufman didn't make it. But it's as you can see, it's like a really super concrete calculation. And you can try to do it for this diagram too, if you have the patience.
What was the little rule you used about the rotation? That the rotation changes the x to a 1 over x?
So let me draw it somewhere.
It doesn't matter how the diagram is oriented, just that you keep fixed. You give names to the boundary points, and you make sure that you don't exchange them. It doesn't matter how you turn it. So if you turn it by 90 degrees, you get the other crossing. Well,
But that did change the x to x inverse, right?
Well, because it changed the diagrams on the right-hand side.
Oh, gotcha. Oh, yeah, it's a 90-degree rotation, so the one that went like this became this one.
Yeah, exactly. So the rule is just by rotating it. So, as you can see, these things are actually pretty fun. So you can ask, if we have an invariant which satisfies OR2 and OR3, can we modify it to satisfy OR1 as well? Now, so this guy, this Kaufman bracket, does not satisfy OR1. But if we have a knot, and we choose an orientation, so my arrows are directed, we define the writhe, or say our link, to be the number of overcrossings minus the number of undercrossings. So for each crossing, we get a count of plus or minus 1. So before, yeah?
Sorry, what's the word you read?
Here?
No, the just before the equal sign.
Writhe.
W-R.
I-T-H-E.
Okay.
the number of overcrossings minus the number of undercrossings. So, well, if we, here, as Alda pointed out, there was only one crossing. Any two crossings can be rotated into each other. But if I draw arrows, there's actually two ones, two distinct ones. So this guy will have a sign of plus 1. Whereas this guy will have a sign of minus 1. And you can see that up to rotating, these are really the only two possibilities. We take whichever strand is on top, we rotate it, so that strand is pointing up, and then the strand at the bottom is either pointing right or left. So for example, here I'm going to leave this calculation on the board. So what was could you guys, I think I just erased it. The answer for this one was that x cubed? Oh, there, it's minus x cubed. Then the second theorem, which is actually not hard. We're given a link. Link L. Let me just draw an example just to make sure I get the. Right, that was plus. This one, the right of this one is minus 1. Then the Kaufman bracket of L multiplied by minus x to the power over the right of L. This is an invariant. So this quantity is the Jones polynomial. Up to some change of variables. There's a variable t, which is maybe square root of x or x squared or something like that. Okay, any questions? Yeah.
I don't know if it's super relevant, but when we have a link, I mean, in general, we're not exactly sure if it comes from, I mean, like we could have a link that is created by projecting two knots and give a link that could look like the link that comes from one knot. Are we assuming here that we want to apply our random master moves to one knot that would give this projection, or
well, the right-of-master moves don't change how many components it has. However, the equations for the Kaufman bracket do change that. So if we want to take this Kaufman bracket picture, we can't change with something just with one component. We can't keep in that world. We might start with something with one component and apply our rules, and it has 10 components. Okay, so I think I should stop in a second, but so the theorem is then the connection between these two things is going to go something like the following. If I take the path integral is going to be equal to the Kaplan bracket times some normalizing factor that only depends on the width, and I don't actually remember it. After substitution, like x is e to the 2 pi I h bar. Something like that. There's some constant here, which I don't remember. So x plays the role of the coupling constant. Okay. So in principle, take the Kaplan bracket, figure out the correct normalizing factor, which is also something easy. Don't quite remember. You expand in series in x. You expand in series in h bar. You should find the Feynman diagram expansion of this expression here. Yeah.
Didn't we want it as a function of the Jones polynomial to be invariant? And
Well, so there's a slightly subtle thing, see, because this guy is not an odd invariant. The Jones polynomial is an odd invariant. The Jones polynomial is the Kaplan bracket multiplied by x to the power some power of the right. This guy is the Kaplan bracket multiplied by x to some other power of the right. So there's some, I mean, the dependence on the framing is some very simple prefactor. But the part independent of the framing is the really interesting part, and that's the Jones polynomial. So you could say the same thing. You're like, it's also equal to some simple prefactor times the Jones polynomial. Yep.
Is choosing framing the same thing as choosing orientation?
No. So if I forget about the planar projection viewed in 3 dimensions, an orientation is a vector along the knot.
Right.
So there's 2 choices, and a framing is a vector orthogonal to the knot.
So in order to define the Jones polynomial, we need to choose an orientation.
Yes.
But it has nothing to do with it.
Yes. Yeah, I can see it's a bit funny. We choose an orientation, then we can define something, and we've got rid of all the framing dependence.
Okay. Wait, and where does the framing dependence come in for this?
For over here,
Yeah.
here it comes in through kind of subtle quantum effects. So,
Just a quick thing, the prefactor has a power of 3 to adjust.
oh, I'm sorry. Yeah.
No, maybe some minus signs, but
No, I think it's that's why I wrote this. I wrote this down to try to make it depends on your convention of what the right is. So this is x cubed. This is x.
yeah.
Yeah. Yeah, that was x cubed, and there was a minus in front of it. So I think that's right. Okay, so next time I'll try to say a little bit about perturbation theory, and we'll try to understand a little bit of why the Kaplan bracket relation you might expect it to hold from the quantum field theory point of view. Although it's hard. I mean,